This is the pre-class lecture for Friday, October 26th. So on Monday and Wednesday of this week, we looked at the mechanisms and all the important information for SN1 and SN2 reactions, as well as what makes a good nucleophile, whether it's going to be strong or weak. And we also looked at, in terms of the leaving group, whether we have a good leaving group or a poor leaving group and what criteria go into that. So the book kind of introduces a topic that's a little early for my taste, but since I'm sort of following the book approach, I'm going to include it in this case, and that is in the next section for the reading assignment is called Rearrangements. And for the rearrangements, I'm going to look at both rearrangements in SN2 and also rearrangements in the SN1 mechanism. And rearrangements are kind of a dangerous topic to talk about because when you see this idea of rearrangements, what you're going to think is that they occur in every reaction, and to some extent they don't. And so they only occur under very rare circumstances. And so here's what I mean by a rearrangement. Let's say that we take 1-chlorobutane and I react it with, let's take an extreme case where I boil it, I heat it in water. Now, what we've learned in the past is that SN2 reactions only occur with strong nucleophiles. And so if this was a primary alkyl halide, which cannot form a carbocation, and so this weak nucleophile can only undergo an SN1, primaries can't undergo SN1. So we'd have to heat this reaction in order to get something to happen. And if we heated this reaction, the only alcohol product that we would obtain would be this one. We actually would not get the water coming in and displacing the chloride. So here's what doesn't happen. What doesn't happen is for the water to come in and kick off the chloride to form then that oxonium ion in a Cl. And then we would lose the H plus, which we talked about for Wednesday. We would lose our H plus, we'd break our oxygen-hydrogen bond to form then 1-butanol. Okay. If a primary alkyl halide would react with a weak nucleophile, this is what would happen. But actually, if you do this reaction, you get none of that product. And so that means that this mechanism that I just drew doesn't happen. Instead, the product that I would observe, if I got any product at all, would be this product. And so the question is, how do we get that product? Well, we get it by a rearrangement, because that's the topic of the moment. So here's what actually happens in this case. What happens is that in the presence of heat in this case, the molecule actually undergoes a rearrangement. Now, what'll happen in this case is that this hydrogen will actually move its pair of electrons over to the chlorine. Okay, now this is not elimination. I'm not losing the CH bond. Instead, what's happening is my H minus here, both of these electrons are actually moving now to form the CH2H bond. So that H is moving as an H minus. That means it's moving as an H with a lone pair. And at the same time then, the chlorine gets kicked out. But this isn't a substitution reaction. This isn't an elimination reaction. Instead, this is a rearrangement. And so this hydrogen is going to move one carbon, and it's going to move towards the carbon that has the chlorine. And so what happens is that we get our Cl minus, but then we also get that hydrogen now attached to the CH2 carbon. And of course, the carbon that was left, that the hydrogen left, now becomes a carbocation. Okay. And this reaction does actually occur. This isn't something that is just done on paper. There is experimental evidence for this happening. And so the H minus shifts over one position, and the chlorine leaves, and we form a carbocation. And in this case, we form a secondary carbocation, which is now stable. So then what happens after that? Well, after we form a secondary carbocation, our water molecule, our neutral nucleophile, is allowed to undergo SN1, so it comes in and attacks that carbon. We form the oxonium ion. And now I'm just going to write this as a CH3 because that hydrogen has indeed moved over. And then in the final step, and I should put my lone pairs on the oxygen. So now the oxygen has its +1 charge. Now I'm going to break the hydrogen-oxygen single bond. And I'm going to go ahead and lose the H+, which would then combine with the Cl- above. And I'm going to form the final secondary alcohol product. And the oxygen now goes back to having two lone pairs, so it goes back to having a neutral charge. So this is an example of a rearrangement. The molecule rearranges itself in order to form a carbocation. And this occurs sometimes, and the word is sometimes, when one has a primary alkyl halide system. You can have the hydrogen move over one position and kick off the chlorine. And that's the only way that we could explain the formation of this product that we might see if we heated water and 1-chlorobutane over a long period of time. Now, this move where a hydrogen moves one position is sometimes, well, it's not sometimes called, it is called a 1,2 hydride shift. Okay. So 1, 2 are the relative positions that the H moves. It just 1, 2 means it moves next to the carbon. It moves to the next door carbon, and then it's moving as a hydride, so it's moving as an H minus. Okay, so this is one example of a rearrangement that we can get. And we'll talk more about rearrangements probably second semester, but this is one of the possibilities. So this occurs, and then what we end up over here with is an SN1 mechanism. And the reason it's an SN1 mechanism is because it involves a carbocation intermediate. That's the big difference between SN1 and SN2 is SN1 carbocation, SN2 no carbocation intermediate. Okay, so that's one type of a rearrangement that we can get. There are others. Let me just change this. Could you write the rearranged product for this reaction? If you think you can, take a few minutes, stop the video, take a minute and see if you can write out the rearranged product for this reaction. It's going to be analogous to what we just did. Okay? Either you stop the tape and you wrote your mechanism out, or you're waiting for me to do it. So let's see what would happen here. What would happen here is that if this hydrogen did a 1,2 hydride shift to kick off the carbon, to break the carbon-chlorine bond, we now would end up forming a stable tertiary carbocation. And now the hydrogen would be attached to that primary carbon. And so then what would happen is then my H2O, acting as my nucleophile, my neutral nucleophile can again react with carbocations. It can do SN1. So now this comes over here, attacks that carbocation. We would form then our oxonium ion. And now that this becomes a CH3. I'm just going to write it as that. And now I've got my oxonium ion. I'm going to bring my pair of electrons, break my OH bond, give my pair of electrons to the oxygen. So I'm going to end up with an H+, and I'm going to end up with my final product. And so there's my final product. So this would be another example of a 1,2 hydride shift. And you might say, why do these hydride shifts occur? Well, here's the best answer that I can give. When we talk about reaction coordinate diagrams and we talk about plotting energy versus reaction progress, we write this as if this was a two-dimensional process or a two-dimensional plot. It really isn't. It's actually more three and potentially more dimensions. Water cannot come in and kick off this CH2 for a number, or kick off the chlorine and react with this CH2 for a number of reasons. You might say, well, here I've got an isopropyl group, so this is going to kind of block the water attacking that carbon in an SN2 reaction, and I would agree with that. But the water itself is not a strong enough nucleophile to kick off the chlorine. So in order to get this reaction to go, we would have to form a transition state that is very high in energy. You know, in order to have this H2O come in and form some sort of trigonal bipyramidal transition state, that would involve a very high energy transition state. And so what happens is this is actually a three-dimensional plot, so that if you're at the reactants and you have some energy that you can go up, there's actually some other hills and valleys that are to the north or the west or the south of where you're at. And one of the lower energy transition states would be to have the hydride shift over and have the chlorine get kicked out. It would turn out that if we wrote that transition state, it would look like this. You would have the chlorine carbon bond partially breaking. you would have the hydrogen partially bonded to this carbon and partially bonded to that one as it slides over onto the CH2 group. And as far as your charges go, this carbon right here is developing a positive charge because it's going to become a carbocation. And the chlorine then is picking up the negative charge because it's on its way to become a Cl-, which I guess I didn't write down here. So this would be the transition state for that 1,2 hydride shift. Well, it turns out that this transition state has a lower energy. It's still very high, but it has a lower energy than that transition state. And so if you give the molecule enough energy, it'll actually prefer to undergo a hydride shift to give me a carbocation than it would to do any kind of SN2 reaction. So the reason for these shifts is the shifts always occur to form a more stable or form a stable carbocation. Look at what happened here. I formed a tertiary carbocation. If I go back to the last example, what did I end up doing? I ended up forming a secondary carbocation. So the issue here is that it's easier for these molecules to undergo this hydride shift and the next shift that I'll show you than it is to undergo some sort of SN2 reaction. And so that's the reason why these shifts occur. These shifts won't necessarily occur at room temperature. You would really need to heat this reaction in order to give it enough energy to form that hydride shift transition state as opposed to the true SN2 transition state. Okay, so that's the reason why the shift occurs, is because that hydride shift is a lower energy transition than is the SN2 reaction. So that's a second type of a shift. Here's a third type of a shift. I'll kind of ease you into these. Let's say I did this reaction. The product that we would predict would be the hydroxide replacing the chlorine here. And that would be the reaction with no rearrangement. But here's the product that people actually got when they did this reaction. They got this rearranged product. How did it form? Well, first of all, this is a secondary halide. And one could make the argument for this reaction that this is a secondary halide where I've got an isopropyl group over here and I've got a methyl group over here. So this carbon we could think of as being kind of sterically hindered. So what if this secondary halide is a little too sterically hindered for the hydroxide to come in and attack it, and instead undergoes SN1 as its mechanism? Could you write the product and the arrow up here to give you the SN1 product? Well, if you do, this is what you get. Plus then you get a Cl-. You get that secondary carbocation. So it's possible that this secondary halide can undergo both SN1 or SN2, right? Because secondaries are in between. So what if it did SN1? What if it lost its chloride? It would now have a secondary carbocation. But here's where the molecule might decide to sort of think and see if it can form a more stable carbocation. And number one, molecules can't think. But if they did, this molecule would sit there and go, if I could hydride shift this hydrogen over here, what kind of carbocation would I make? Well, the molecule would go, well, if I can do a 1,2 hydride shift, then that would leave this carbon as now a tertiary carbocation. So I would actually, at the end of the hydride shift, end up with a much more stable intermediate. And so if the molecule did this, then what would the hydroxide do? The hydroxide would then come in and attack the carbocation, and we would end up with now our final product, which is the rearranged product of the reaction. So notice what I did here. In the first two examples, I started with taking primary systems and doing a 1,2 hydride shift to form either a secondary or a tertiary carbocation. What I'm doing in this case is starting the reaction out as an SN1, but then if I have a secondary carbocation and I could shift this hydrogen over to form a more stable carbocation, then the molecule would do that, and then I would have my nucleophile finally attack to give me the rearranged product. Okay. So this is an example where it starts SN1 and then undergoes the rearrangement in that second step. What's the driving force for this reaction? The driving force for this reaction is to form the more stable tertiary carbocation than the secondary carbocation. Okay, so this is another type of rearrangement that we can have from secondary carbocations to tertiary carbocations. We can't have primary carbocations, and so we can't have primary carbocations shifting into secondary or tertiary carbocations. That's not allowed because primary carbocations aren't allowed. But we could have secondaries shift over into tertiaries. Okay. So could you write this mechanism for this molecule showing a rearrangement? Okay. This is the same molecule that we used before. So this is going to undergo neutral nucleophiles, only undergo SN1. This is a secondary halide, and so that's perfectly able to form a carbocation. So the first step, break the carbon-chlorine bond to form my secondary carbocation. And now do what? Do the 1,2 hydride shift to now form the tertiary carbocation. And now my water comes in and attacks. And remember, it's the whole water molecule that comes in and adds to that carbocation. It donates one pair of electrons to form the bond, which means that it picks up the positive charge. Now I'm going to write that CH with the H into a CH2 group. And now what's going to happen with this? That lone pair is going to be given back to the oxygen. So I'm going to lose the hydrogen as an H plus to then form my final product, which would be this, and this would be my rearranged product. Turns out it's the exact same product that we had last time, only this time I used a water molecule. Okay, so these are examples of 1,2 hydride shifts. Okay. Now, hydride isn't the, or hydrogen isn't the only thing that can shift. And one thing that I'll say about this reaction is hydrides can only shift one position. And if they're going to shift, it has to be to form a more stable carbocation. And in this case, we've got the secondary carbocation going to the tertiary one. So hydrides can shift, but it also turns out that methyl groups can shift. So that, let's say I had this molecule. Now, if we look at this molecule, we can see that this is a primary alkyl halide. And primary alkyl halides can only undergo SN2. They can't do SN1. But this hydroxide then would have to do backside displacement on this carbon, and one could make a very good argument that this terse butyl group here might block the hydroxide from coming in and attacking that carbon with the halogen leaving group on it. Now what that really means is it would raise the energy of the transition state to a point where there's another type of rearrangement that we could get for this reaction, and that's called a 1,2 methyl shift. And so in this case, what can happen is that this methyl could move with its pair of electrons. So this is moving as a CH3 with its lone pair. Okay, and that would be 8 valence electrons. So what could happen is the methyl group could slide over, and then the carbon-chlorine bond would break, so that I would do this 1,2 methyl shift. That would leave this carbon with 3 bonds, which means it would leave it with a +1 formal charge. Now this CH3 group would end up here, and I would end up with my Cl-. And so after this rearrangement, why did this rearrangement occur? To form a stable tertiary carbocation. The hydroxide then would now come in and add its pair of electrons to the carbocation, and we would form the final rearranged product, which would now be this one. So this is our rearranged product. Okay, so it's possible then to also do 1,2 shifts with methyl groups, and you can do a 1,2 methyl group shift. These are sometimes called, and I may use the term migration as well, a 1,2 methyl migration. Okay, so could we do this with a carbocation like we did before? So could I take, for instance, this molecule and react it with water? Could you, after seeing these examples, write the mechanism and write the rearranged product for this reaction? If you think you can, take a minute, write the mechanism, and write the final product. Or what I'll do here in a moment is I'll write the product, the rearranged product, and then you can see if you got that right, and if you got that right, then stop the tape again and write the mechanism. So here is the final rearranged product for this reaction. Okay, there's the final rearranged product. So can you now write the mechanism to get that product? Well, what we would do is we would break the carbon-chlorine bond. This is a secondary halide, which can form a carbocation. Water, being a neutral nucleophile, can only undergo SN1. So we break that carbon-chlorine bond, and we form our secondary carbocation. Now again, the molecule looks and says, if I could shift this methyl group over here and do another 1,2 methyl shift, then I could say, oh, I would get a tertiary carbocation. So I went from a secondary carbocation to a tertiary carbocation, which means that the driving force for this reaction is the formation of the more stable carbocation. And then my water would come in. And again, the whole water molecule would come in and add to that carbon. So I'd get my oxonium ion. And then this pair of electrons would move here so that I would lose my H+. Take that pair of electrons, give it back to the oxygen. And so there would be my final product. Okay. So when we talk about rearrangements, let's kind of just summarize this. So the important thing about rearrangements are that number one, that you're going to shift either a hydrogen or a methyl group to the next or attached carbon. And that's going to be a carbon. This carbon is either going to have the leaving group attached, or it's going to be a carbocation. So you're going to shift the H and the CH to the next carbon, and that carbon either had the leaving group attached to it, or it is now a carbocation. So again, by shifting it to the next carbon, that's where the 1,2 comes into play. It's moving relative position from 1 to 2. So that's the first important thing to remember. The driving force is to always form a more stable carbocation. So either you go from a primary alkyl halide to a secondary carbocation or tertiary carbocation. I actually didn't give you an example of one of those. Or you go from a secondary carbocation to a tertiary carbocation. So that's always the driving force for the rearrangement. And then after that, after the rearrangement, you have then an SN1 mechanism. Okay, so those are the three key things to remember about rearrangements. Now, the last part for this lecture for Friday is to compare SN1 versus SN2. Well, we've already compared their mechanisms, right? One step versus either a 2 or 3-step process. Concerted one-step mechanism versus formation of a carbocation. No intermediates versus 1 or 2 intermediates. Producing optically active halide produces optically active product with inversion of configuration, or optically active product or optically active reactant gives a racemic mixture. Okay, so we can compare the reactions in those terms, kinetics unimolecular versus bimolecular. But what I want to really compare is this. How do I know if a reaction will go? Will the reaction proceed? I should probably put a will here. Will the reaction proceed by SN1 or SN2? Well, what do we know about these SN1 and SN2 reactions? Let me ask a question. Primary, secondary, and tertiary alkyl halides. Which mechanism can they undergo? If I said, what mechanism can a primary alkyl halide undergo, you would say, come on, you can say it, SN2 only. If I said a tertiary alkyl halide, what mechanism can it only undergo? SN1. Secondaries can undergo what? SN1 or SN2. Why can a primary halide only undergo SN2? Because it can't form a primary carbocation, and it's not sterically hindered enough to have the nucleophile be blocked from backside attack. Why can a tertiary halide only undergo SN1? Because it's too sterically hindered to have the backside attack of the nucleophile, and it forms a perfectly stable carbocation. Secondaries are kind of the middle child here. They're the ones that can do either or. And they're the ones that kind of become a little bit of a problem because there's a lot of exceptions to the secondary halides in what we would predict. But if we focus on the exceptions, then we're not going to learn the rules. So I'm not going to do the exceptions right at the moment. So here's what we know in terms of an alkyl halide. Now, what do I know about the nucleophiles? What kinds of mechanisms can strong nucleophiles undergo, and what types of reactions can the weak nucleophiles undergo? And remember, weak is either water or ROH for an alcohol. So which reaction do they undergo? While I'm correcting it, make a decision. So, strong nucleophiles can do what? They can do SN1 or SN2. What reactions can weak nucleophiles undergo? SN1 only. In other words, the weak nucleophiles can only react with carbocations. And I haven't said this so far, so I'll take a minute here to say this. Remember that the nucleophile electrophile reactivities are basically the most philanthropic things that you can have. In other words, in chemistry, the electron rich give to the electron poor, and the electron richest give to the electron poorest. Well, when I have a weak nucleophile, that means it's not very electron rich. And so it can only react with the poorest of the electrophiles. In other words, the ones that have the greatest delta plus charge. Whereas the strong nucleophiles can react with carbons that only have delta plus charges, or they can react with full-blown positive charges. The weak nucleophiles can't react with weak electrophiles. They can only react with strong electrophiles, things with full-blown positive charges. Now, we've laid out the rules here. Primary halides undergo SN1 or SN2. Primaries only go SN2, secondaries SN1 or SN2, tertiaries SN1. Nucleophiles, strong nucleophile, either, weaks SN1 only. So let's draw a little chart down here. And let's say that I have my alkyl halide down this column. So primary, secondary, tertiary. And over here, I'm going to break this chart down into strong nucleophile, which means it's got a negative charge. Weak nucleophile, which means that it's either water or alcohol. It's neutral. Can we tell what type of reaction I'm going to get for the primary halide plus strong nucleophile? What mechanism is going to occur here? So primary alkyl halide plus strong nucleophile. What do you think? You said SN2, you're right. Secondary halide plus a strong nucleophile. Well, here you could say SN1 or SN2, but in this case, since we have a strong nucleophile, I'm going to say SN2. Tertiary halide plus a strong nucleophile. What mechanism am I going to get here? SN1. Why? Because tertiaries can only undergo SN1. Now let's come over here. Tertiary halide plus weak nucleophile. What's my mechanism there going to be? SN1. Why? Because only tertiary halides, they can only undergo SN1. How about secondary halide plus weak nucleophile? What mechanism am I going to get? If you said SN1, you're correct. Because while secondaries can undergo SN1 or SN2, the weak nucleophile can only undergo SN1, which is okay because the secondary halide can form a carbocation, which will let it undergo SN1. Now here's the tricky one. What happens when you try and react a primary halide with a weak nucleophile? What do you get? No reaction. And then somebody says, but wait, way back here, you started us off with this reaction. Okay, if the molecule can rearrange, then you'll get a reaction. Okay, but if we say that it doesn't rearrange, then no reaction. So this chart then allows us to predict the mechanism for the way the alkyl halides react with a nucleophile. So let's, as our final thing here, before I put some of these kinds of problems on the quiz, let's draw some reactions and say, okay, can you identify what mechanism each of these reactions undergoes. Take a minute. Which mechanism is the first one? If you said no reaction occurs, you're correct. How about the second one? What do you think? I say SN2. Third one, I say SN1. Did you get all three of those right? Or are you sitting there going, where did he get those answers? Well, what I did was I said this. This is a primary halide plus a weak nucleophile. I now go back to my chart. Primary halide and a weak nucleophile is no reaction. I look at this one, secondary halide plus what kind of nucleophile? Strong. Remember, our basic definition of strong nucleophiles, anything with a negative charge. Weak, neutral. The only neutral ones we have right now are water and alcohol. So I got a secondary halide plus a strong nucleophile. On my chart, secondary strong nucleophile goes by an SN2 mechanism. Tertiary halide plus H2O. Tertiary halide plus a weak nucleophile. It's automatically SN1 because that's the only mechanism that either of those two can undergo. Okay, so after we learn about SN1 and after we learn about SN2, this is the point where we kind of put those two reactions together and we say, if I give you a reaction, if I give you a halide with a nucleophile, can you tell me what the mechanism would be? And of course, for these two problems right here, the question is, could you write the mechanisms of those SN2 and that SN1 reaction? Could you write those mechanisms? And I'm assuming here no rearrangements. And just my last word on this will be that the problem with rearrangements is that once you see them, you think they occur every single time. And then the people that write book problems in the back of the chapter are different than the people who write the book, and so they decide that they're going to throw in random rearrangements all the time. And so then you're left with confusion as to when do rearrangements occur, because I can't figure out a pattern from the book or from the problems at the end of the chapter. So what we say is this. I will tell you when a rearrangement occurs either by saying, write the rearranged product, or if it's a mechanisms problem, I will give you the final rearranged product and ask you how to get there from the mechanism, and at that point you have to recognize there's a 1,2 hydride or a 1,2 methyl shift. And that gets you your final product. Okay? So, in class, if there's questions, we'll talk more about this, but I can give you some reactions and say, tell me what mechanism they are, and more importantly, can you write that mechanism out? And then we'll do some rearrangements to write the rearranged product as well as write the mechanisms for the different kinds of rearrangements. So that's what we'll do. So there will be an online quiz, and that will probably be posted probably on Wednesday afternoon. Okay.